Okay, let me know if sound is coming through now. If it is, just give me a thumbs up in the Slack. Still no sound? Okay, great. Awesome. Yeah, I set up like a pass-through audio earlier, and I thought it was working, and apparently not. So I just I'll have to set that back up later. Okay, so we're looking at this basic string properties challenge, and we're going to write a function called isNumber. I'll just start writing that now. Def is number, and that's going to take a string as an argument and returns the type as a string if the string is indeed a number. Okay, so we're going to put in something here called I don't know, num string, I guess I could call it that, and it'll return the string not a number if the string is not a number. So let's look at these expected results. Okay, so 3.1 is a float. Sure. This is not a number. This is not a number because it has 2 decimal points. So I'll show you how, just a quick way to solve this. We could think about valid characters first. And, you know, we could just make a string of valid characters. And of course, this is going to be these and the decimal point. And I could say something like, for, I don't know, character in num string, if the character is not in the valid characters, then let's return not a number. And if this completes, then we can return the string. I'll just do string of the type of the num string. Now, this won't totally work, and it won't work because we've got this situation where we've got double decimal, double, periods in there. So we also need to account for that. I could just make another quick statement here. I could say if num string dot count of period is greater than 1, then return not a number. So that should work as well. And let's just find out if this works as is. There might be something I'm missing in here. Ooh, it failed. Okay. Oh. Huh. Okay. So let me show you this. Oh. Okay, I just need to do a couple more things here. I was kind of thinking about this in a strange way. If it's a float, then it'll have a decimal value in it. So if I can just say if a decimal point is in the num string, right? Because I've already got these returns. I've already accounted for if it's not a number. If there's a decimal point in num string, I can just return float. And I think otherwise I can just return int. I don't know if we're trying to account for some other kind of number here, but yeah. Yeah, let's see. Let's see if that works. Okay, it failed. Int does not equal not a number. Okay. So somewhere I'm letting something pass through. That is not a number. So let me see if I can get this to print out. Let's try this. I'll just print the num string here. See if I can get a little bit of diagnosis on what's going on here. Oh, I'm not getting anything out of that. Okay, well, let's try to track this down in a different way. Okay, so this should be working, else return int. I'm assuming we're only dealing with floats and ints, is that right? Yep, either an int or a float. And if the count is, okay, so can we make an invalid number with these? Huh. Yeah, I'm not. Oh, empty string. There we go. An empty string should be considered not a number. So I'll just put an or in here. Or the length of the num string is 0. Or I could say if, you know, num string double equals 0, double equals empty string. That would work just as well. So let's see if that works. I think that's probably accounting for it. Yeah, there it is. So this is a little bit of cleaner code than what I wrote. Let's take a look at this. All right. So handling an edge case if not string or string.count of period is greater than 1. Okay, so we did that. We just didn't do it at the same time. Check each character. Okay, so we did that, but in a different moment. And yeah, and then essentially the same thing, right? If there's no period, we're assuming it's an int, and if there's a period, then it's a float. Cool. All right, so let's take, I think there are some other people who posted questions. Okay. Intermediate Python string functions and methods replace. Okay, let's take a look at this. And we're looking at write a function called replace doubles. Okay. So write a function called replace doubles. This function takes a sentence as an argument, then checks for any double letters, for example, AA or TT, and replaces the double letters with just a single instance of that letter. Okay. It should be case sensitive, so preserve the case of each letter. Like a big A, little a would not be considered a double. The space character may also be doubled and should be replaced by a single space. Okay. So let's think of how to write this. So we're writing replace doubles, and it's going to take a sentence. So I'll just call it sentence. And let's think of how to do this. Here's an easy way to do it. Let's make, I'm just gonna make something for our output that's gonna be out. And I'm gonna say for, let's set a prior character. The prior character is gonna get the first character in sentence, which is the 0th index. And I'm gonna say for character in sentence, and I'm gonna just start from the next position on until the end. I'm going to say if character is the same as prior character, then we want to continue, and otherwise, oh, well, first, let's see, is this gonna work? Well, let's just try it. Okay. Otherwise, we're going to set the prior character to the character, the current character, and we're going to, first we're going to concatenate the current character to the out string, and then the prior character is going to get the current character. Yes. So let's return out. And how about I just write some tests for this? So I'll do that. I'll say, let's print this, and I'll just make a couple of these. Oops. Let's do 3 of these, and I'll do A, T, B, A, something, 2 spaces, and UU, or LL, that is, and some letters. Let's just try that first and see what we get. Okay, that looks, oh, I see. We aren't going to include, because we want to replace a double character with a single character. So that's actually not going to work for our purposes. It won't work just for the first character. That's the issue. Okay. So let's think about how to solve that. So we have this prior character for each character in the sentence, starting there. Oh, why don't we just put the first letter of the sentence into the out. Let's see if that works. Yeah. And then, yeah, so the logic here, we take that first letter and we put it into out, and then we set the prior character to that as well. And then for every character after that, we can simply check to see if the character is the same as the prior character. If it is, then we don't do anything. We just continue. And then, am I sure this is working? I think it is. Let's find out. Let's run it against the actual tests. I might be off in my logic here. Oh no, that worked. Let's see how. Oh. Now this is cool. Okay, this is a completely different way to do it. Let's take a look at this. I like this. I like this solution. This will always take the same amount of times to run, but it is a completely different way of solving the same problem. Here, it's cycling through the characters, and it's saying that in any case where a character is doubled, it'll just, which is what this means, like letter times 2, that'll be a string with 2 of the characters. At any time that happens, it's going to replace it just with that letter. So that's really cool. Completely different logic, but gets us to the same outcome. I think for short sentences, this is better. This is more performant. For longer sentences, this would likely be more performant, because this has a cap on the number of times it'll run. So yeah, that's a cool solution. Okay. All right, so challenge 3 in traversing a list. In general, when you ask a question, if you could put a link to the problem too, that would be really helpful. But let me see if I can track this down. Okay, this is in challenge 3 in traversing a list. So I think this will be under list iteration, traversing a list, then challenge 3. Okay, looks like I got that. Okay. So in the code cell below, use list iteration to accomplish the following. In a list called even nums, append all the even numbers from the original list, iteration list. Similarly, in a variable called even index, collect all the values which are associated with the even indices in the original list, iteration list. Okay. Let me just grab this. All right. So we've got this iteration list. And we're going from 1 to 1,000 by 3s. And we're going to make a collector called even nums and another one called even index. So let's just get even nums first. So even nums, and I'll just make this an empty list. And I'm going to iterate over this iteration list. So for num in iteration list, this is any numbers that are even, right? I'm going to append. So I'm going to say even nums dot append the num, and that'll be under the condition if num modulo 2 is 0, then we're going to do that. Okay. If I go ahead and print the even nums, should be able to see something there, right? These are all even numbers, and it makes sense because we're starting at what, 1, and we're going to 1,000 by 3s. So so 4 and then 7 is not even, then 10 is even, then 13, then 16 is even, and we can kind of see why that would work. So even index is the other collector that we're going to have here, and you know, if the number modulo 2 equals 0, even nums.append num, sure, but we also want the index here, right? So every even index we're going to also grab. So for index and num in enumerates the iteration list, we're going to first check if the number modulo 2 is 0, then we're going to check if the index modulo 2 is 0, and I'm a big fan of copy paste, so I'll just do that, and I'll say num, I'll change num to index idx, and even nums I'll change to even idx. So we should be able to see both of these now. Okay. So that makes sense, and it's just using two different pieces of logic to perform this collection. And let's see, I'm gonna put this in here, see if this works. There's a chance that this is, oh, no, it works. And it looks like what they have here is pretty much exactly the same thing. The only difference is I went ahead and did both operations in a single loop, as opposed to doing two separate loops. Okay. And so let me grab your code and let's troubleshoot your code and figure out what's going on here that is different. So even nums, even idx, so that makes sense. For x in iteration list, if x modulo 2 is 0, even nums.append x. For I in range 1 to the length of the iteration list, there isn't a good reason to start at 1 here. you actually just want to say the range of the iteration list. And you don't need to go by threes because this was already generated that way. So you can just get rid of those. And I think you can just say, instead of if iteration list sub I modulo 2, you could say if I modulo 2 is 0, then even index.append I. So I think that should work. Let's see. Oh, what's wrong there? First differing element. The length of the iteration list for I in range, length of the iteration list. If I modulo 2 is 0, even index.append I. What am I missing here? It's probably some simple thing that I'm not seeing. Even nums.append x. So this should be right. Yeah, that's interesting. But let's print the iteration list. And the first number in this iteration list should be 1, right? So if I modulo 2, I would expect the first value here in even index to be 1. And for some reason it is 0. Oh, because we're appending I. That's my fault. I just overlooked that. We actually want to append iteration list sub I. And I think that'll work. Yeah, that worked. Yeah, so there were just a couple things off about this. You didn't want to append the index. You wanted to append iteration list sub I. Actually, I think I may have made that change. No, I think that was in the original code. So there was that, and we're checking the index, the evenness of the index. That's what we're checking. And if that is even, if the index is even, then we can append the value to even indexed values. Okay. Let's look at another one. The last two problems on the beginning of the self-placement challenge. So I don't tend to solve the self-placement challenges. Those are for your study purposes. But I wonder, I'll take a look at it, and let's see if I can kind of explain this without. Okay. You know, I might just solve this. It looks interesting. So there's that, and then find primes. According to, okay, remember to take care of that. Okay. Yeah, so I'll go ahead and solve this. Remember, just in general, the self-placement there is there, you know, so you can go through it, and if, you know, if you breeze your way through it, or you get stuck on a certain thing, you get some indication of where to put your studies. That said, let's go ahead and solve this. Just fair warning. Okay, so we're going to test a number. If n is odd, triple it and add 1. If n is even, take half of it. Repeat this process until the number 1 is reached. Return a list of all numbers that were iterated through. Oh, okay. All right, so I'm going to make something called nums. And we're going to take n, and we're going to say while I'm going to make a copy of n because I don't want to modify the parameter. I'm going to say I'll just do n underscore is going to get n. And I'm going to say while n underscore is not equal to 1, right? Because that is our base condition. Repeat this process until the number 1 is reached. So if n is odd, that's easy. Well, we can answer that. If n modulo 2 is 1, if n is odd, then take half of it. And we're not dealing with n, we're dealing with n underscore. So then n underscore is going to get divided by 2, right? If n is odd, triple it and add 1. Let me do that instead. So I'm going to say, well, I'll just do this. Is going to get n underscore times 3, tripling it, and then adding 1. If n is even, actually, should just do else here, right? If it's not odd, it's even. If n is even, take half of it. And if at anytime we do this, we want to, anytime we do anything, we want to append it to the list. So the ambiguity here might be, well, do we take n and do we include n in this list? I'm going to assume that we do. And then if not, I'll fix it. So in any case, whenever we modify this, you know what I can do? I can just put my append up here. Yeah, I'll do this. I'll do nums.append, and I'll append end underscore, and then I'll return nums plus n underscore, because I'm assuming that'll be our last value. So I might be being too careful about this. Let's see what happens when we run tests on this. Tests canceled. Okay. So let's just look what happens when we run this locally. I may have made, you know, sort of a infinite loop here. I'm going to put this doc string over here and just delete the doc string because I keep having to look up and I kind of want to see everything in one place. So let's say, let's print wondrous test on, let's do 12, and let's do a few more numbers as well. So 12, 2, 4, I don't know, 7, 8. And oh, okay, yeah, that seems, here, let's try that. It looked like I used n instead of n underscore for one of those. So let's test that and see if this works now. Oh, okay, yeah, so my logic was fine. So what are we doing here? The first thing is I'm making a copy of n, and then I'm going to have this collection list, and I'm just going to say while n underscore isn't equal to 1, I'm going to append n underscore to nums, and then I'm going to either triple the number and add 1 or divide it by 2, and eventually that's going to get us down to 1, and then that'll break us out of this loop. And then the last number we iterated through, we didn't really iterate through it. If if you imagine, because that was just the final number. Either way, just in terms of the description, I'm going to take this nums list and I'm going to concatenate it with a length 1 list that contains n, or n underscore. Okay, so I'm going to go ahead and reset that input, and I think this is the other one, this find prime function. So let's take a look at this. Finds all prime numbers within an input list and returns those primes in another list. Okay. List of all primes in the list. Okay. So we're going to iterate through list, right? So for num in list, and I'm going to make a collection list here called primes. I'm going to say for num in list. Oh, you know what? Sorry, let me back up. There are a couple questions on that prior function, so let me just answer those. All right, so the question is, you don't understand returning nums plus n underscore. Why in brackets? So I put this in brackets because I'm just concatenating nums, which is a list, with n underscore. And n underscore contained in a list, that'll just put it at the end of the list. So the other way I could have done this, I could have just done this, nums dot append. I could have done n underscore there, and that would work the same. Either way is fine. All right, so let's try this again. So we're going to find all the primes within an input list and return those primes in another list. So that other list is primes. I'm just going to name it primes. And I'm going to say for num in LST, if is prime of num, well, if it is, then primes dot append the num and return primes. Okay, well, we're missing something, right? We're missing this isPrime function, and I'll just go ahead and write that. So this is one of those functions that we say, hey, you should probably be able to write this. If the way that you can do this, you can do it using an iterative approach. We can deal with edge cases. So first, so if num is less than 2, or num modulo 2 is 0, then let's go ahead and return false. And otherwise, we're going to say for, I don't know, divisor in range num divided by 2 plus 1, and this should be an integer. And we should start at 3, okay? And we should go by 2, okay? So we're starting at 3. We're only going to check. Oh wait, am I thinking about this wrong? We've already checked for 2s. No, I think this is right. Okay, so for divisor in range from 3 up until half of the number plus 1, let's say, and we're going to go by 2. So we're going to check 3, 5, 7, 9, etc. And let's see, is this going to work for 3? Yeah, this should work for 3. It's not going to work for, okay. It's not going to work for 2. So I'm just going to say if num is 2 or num is 3, then return true. I'll just do that, and that'll kind of cover those cases. So I have some error somewhere. Oh, I see. I'm going to say if num modulo div is 0, return false, and then at the end of this, I'm just going to return true. Okay. So let's try this. It failed. Oh. If the list is empty, we need to return no prime found. Okay, well, let's do that. So for find prime, I'll just say if the length of primes, actually, yeah, if the length of primes is 0, let's just return no primes found. Let's try that again. Still failed. The second list contains one additional element. 2, 3, 5, 7. Huh. Let me see. Three, 5, 7 is not equal to 2, 3, 5, 7. Am I not? If the number is 2 or the number is 3, return true. There's something wrong with my is prime function, I think. Let's see. Oh, I think somebody else did ask about find primes. Yeah, and yeah, you're the one. Yours is next. Yeah, I think I've solved that one before, the twin primes problem. I think it's pretty cool. So we'll look at it in a second. I'm going to go ahead and simplify this is prime function because I must have done something a little weird in here. I'm just going to say I'm going to leave this first condition, and I'm going to say for divisor in range, and I'll just do the range of the num, if the number modulo the divisor, then return false, otherwise return true. So that's a much simpler is prime function. It's not as optimized, but I think I must have put something in my other is prime function that was a little wonky. Huh. Interdivision or modulo by 0 if num modulo div. Well, that makes sense because I want to go from 2 up until the number. I do not want to divide by 0, which modulo division by 0 is still division by 0. Let's try that again. Huh. No prime found not equal to 2, 3, 5, 7. Okay. I wonder if there's something going on with the test here. I'm just going to open this test up really quick, take a look at it. I mean, in all likelihood, I'm just doing something really weird somewhere that I'm not noticing, but let me just make sure. Okay, so this is find prime. Okay, so looking at the tests, I'm just going to grab these lists and test them all individually. So let's do this. And I'm just grabbing these directly from the unit tests that we have for this problem. And like I said, in all likelihood, I'm just not thinking clearly and I have some error. But I'm just going to run these by our actual tests just to confirm that. And okay, so let's try that again. And I'm getting no prime found for everything. If is prime of num, if num modulo div return false. You know, this is one of those moments where I should just honestly test my is prime function. So we would expect 13 to be prime, and notice that it's returning false. So let me just walk through this. If num is less than 2 or num modulo 2 is 0, return false. So that takes care of evens and 1 or less than 1. For each divisor in the range from 2 up until the number, if the number is divisible, oh. Yeah, okay. Let's try that again. So we're expecting to see, so the error I made here, I said if num modulo div, and what that means is that if this is not 0, then this is going to evaluate to true. And so I was sort of inverting the logic. I just forgot to put double equals 0. Okay, so let's look at these. We would expect no prime found, right? That's what we get. We would expect 2, 3, 5, 7. Oh, interesting. Well, that makes sense. I need to just put another condition in here that's if the number is equal to 2 or the number, I don't need to do is equal to 3, but I might as well. I mean, it'll work like this. So we just want to make sure we cover the case of 2. Okay. So that would account for that issue. And that would also account for this issue. And then this last one, it would account for this as well. We should get 2, 3, 5, 7. Yeah, okay. I think this is fine. And we've got a working as prime function. I usually write those optimized. I don't know, my brain's not 100% apparently at the moment. So let's try that. Let's see if that works. And it failed. 2, 3, 5, 7, 3, 5, 7. Okay, what is going on there? If the number is 2, return true. Okay. Let's try this again. Let's look over here and see what we get. We're still not getting 2 out of here. Okay. Why is that? What am I doing wrong here? If the number is equal to 2, return true, right? What am I missing? Is it something in here? I am really baffling myself right now. Does anybody see what I'm doing wrong here? Like, can't be much more explicit than that. Oh. Okay. Okay. Right. If I'm gonna check evenness divisibility, I need to do that before. I need to do that after I check to see if the number's 2. My bad. Okay. So now that works. It was just a silly logic error on my part. Let's try that. Yeah, That's where the issue was. So if it's not clear where the issue I was having was, I was checking for num modulo 2 equaling 0. Of course, 2 modulo 2 is going to be 0. And yeah, it's just silly. I have to account for num equals 2. And when I'm thinking about it, that's what I had it in the other order before when I had this is prime optimized. But either way, it's working now. This is not an optimized function, but that's okay. Why don't we optimize it a little bit? Why don't we say from 3 to num divided by 2 plus 1, and we'll make that an integer, and we'll go by 2's. So let's see if that is the optimization. Yeah, this is a faster function, just because we cut out a lot of values. So yeah, let me just make sure I didn't overlook something. I'll run it again. And this function is going to come in handy in the next problem, which is the twin primes problem. So I'll leave that up. I'll leave is prime as it is, and we'll look at some stuff. All right, so in basic Python, while loops, open-ended problems, and this is the twin prime conjecture. Okay, great. Okay, twin primes. The twin prime conjecture is a theory in which there are an infinite something. I'm going to assume it says number of primes, pairs of primes that differ by 2. This function finds the nth twin prime pair. For example, the 5th twin prime pair is 2931. So we're going to return a list which is the nth pair of twin primes. Okay. So I'm going to just grab all of this, just put it over here, maybe make it a little smaller, and it'll just be a little easier to see. So we already have our is prime function. We don't have to worry about that. So we want to capture our twin primes, and so what's a good way to do this? We could probably do this in a fairly brute force way. Yeah, why don't we do that? We'll start with that. So I'm going to build a list of primes, and I guess I could use some of the logic that I used earlier. So why don't I say, I'll just say twins, and this is going to be an empty list, and I'm going to, oh, I know what I'll do. This will make it kind of nice. Let's write a function called next prime. And we'll start with some number. And we're going to assume, I guess we don't have to assume this number is prime. No, we don't need to. So I'm going to say while, I'm going to make a copy of this number. I'm going to say num, actually, let's get the next number. So I'll just say, I'll call it n, and this will be num plus 1. No, let's actually just get num. That makes more sense. Okay, so while That's a good way to think about this. I'll just make an exit condition. I'll say while true, and we'll tidy this up in a second. So while true, I'm going to say, well, we want to start with, yeah, we do want to start num plus 1, don't we? So why don't we say while is prime of n is false. Or we could say while not is prime of n, right? Then we're going to, yeah, we're just going to increment n, right? Am I being silly here? I might be being silly. Hold on. Let's find out. So let's get the next prime from 2. And just find out what that is. So 3, that works. Let's do 12 is 13. Let's do 13. 17, okay, this looks like it's working. 19, okay, that sounds good. All right, so we're going to return, sorry, we're going to pack in, oh, let's look at what this is asking one more time. We're trying to get the nth twin prime pair. Okay. So our first twin prime pair is going to be 3, 5. And then our next one is going to be 5. Bring this to be our first twin prime pair, our second twin prime pair, and I think that's how we're looking at this. So we want to start at 3. So I'm going to say for, well, I guess we need to do a while. So we'll call this position, and we'll start position at 3, and we'll make a counter. Let's call this num to check. Num to check. Call it 3, and we'll say position is going to start at. I guess we start at. Let's just check the length of twins against nth, right? So the length of twins plus 1 is going to be the nth position. So while length of twins plus 1 not equal to nth. How about that? And I'm going to say if next prime of the number to check minus the number to check equals 2, then twins dot append, and let's do number to check comma next prime of number to check. Is that what we want to do? You know what? This is just, it's gonna look a little messy, so let's I'll call this next prime, because we're going to want to use it again anyway. So next prime is going to get, oh, let me give it a different name. I'll just call it next. So ooh, I can't use next. I'll just call it next underscore for the sake of time. So next underscore minus num to check is 2. If that's the case, then twins.append number to check and next as its own list, right? So this is going to be a list of lists, and after we do that, either way, we want to replace number to check with the next value. Okay. And then we want to return the nth pair of twin primes. I think we just want to return twins sub -1, the last value in there. Okay. I would be surprised if this is working as we expect it, but let's find out. Let's test it out, you know. So print twin primes of, well, let's get the first twin primes. Let's see what that looks like. List index out of range. Okay. On line 63, return twins sub -1. Let's just return twins and see what that says. Oh, we're not going to get the first value here. That's why. So twins, let's just pack in the first value. And let's say 3, 5. And while the length of twins plus 1 not equal to nth. So let's try that. And then it ran forever. Yeah. Okay, so what am I doing there? This has the length of twins plus 1. That would be 2. And nth equals 1 there. So if nth equals 1, we're going to want to return 3, 5. It's a good way to trick that. What's a good way to get around that? I could just ask if nth equals 1, and that would get us past that first one. That's a little silly. Let's see. Why don't I do this? Why don't I make something called position? And position is going to start at 1. And while position is less than nth. So let's try that. And so that gets us our first value. And num to check. So we need to do something here too. We need to increment position every time we append more numbers. So we're looking at our first position. Let's look at our second position. Still getting 3, 5. Okay. Now why is that? We should get 5, 7. So num to check gets 3. Position next gets next prime. So let me print while position is less than nth. Okay, I'm getting 3, 5 twice. Is that because I'm starting at that? Let's try that again. Okay, that's why. Because I was starting at 3 still, which makes sense. So position less than nth. Let's get the last value out of this. This is a cool problem. It's harder than, I think I've solved this problem before, and it's still pretty tricky. Yeah, this looks like it's working now. Okay, so it says here the fifth twin prime pair should be 29 and 31. Let's see if that's the case. Let's see if we're getting that. 29, 31. Hey, that looks good. So all of this, as you noticed, all of this depends on this twin. Oh, I think I just collapsed all of this. Okay, this next prime function, right? Where I just grab the next prime and then I can subtract the current prime from the next prime, and if that equals 2, then I can get that. I can append it. So let's see if that passes the tests. And it did. Let's see how this code does it, and I'll pick this apart. Oh, it looks like it's a similar approach to what I did here. Okay, so we've got twin prime of nth, and prime 1 is 3, prime 2 is 5. We've got a pair counter, right? This is sort of like the position that I used. While pair counter is less than nth, prime 1 gets prime 2, okay? And prime 2 gets next prime of prime 2. If prime 2 minus prime 1 is 2, pair counter plus gets 1, return prime 1, prime 2. So yeah, the real difference here is that it's got sort of these temp variables that are swapping the whole time. What mine is doing is building a list and then just returning the last element of that list. So either way is valid. I think the way that I'm doing it is nice if you are checking the length of the list and using that as your break condition, which I was doing and then I changed it because I was troubleshooting. And then for next prime, it just collapses both next prime and is prime into one function. So it's still using that helper function. Okay. All right. Yeah, so hopefully that gives you a path forward with the logic for the twin primes problem. And if you want me to go back over any of that, just let me know. I'll leave this code up so we can get back to it. Okay. Question on break continue pass breaking loop challenge 3. Let's look at that. Okay, challenge 3. Complete the find. Oh, it looks like this is another one. Wait, really? This is another one using primes. Here, I'll just reset the input here. Complete the find primes function according to its docstring. Wait, did no, we didn't just do this. No. Okay. There's just a whole lot of primes happening today. All right, so finds all prime numbers in nums and returns those primes in a new list. Oh, no, we did do this. I'll just solve this really quick. We already have an isPrime function up here. Okay, so the way that isPrime works is first I check to see if the number is 2, the number that we've inputted. If it is, we just say it's true. If the number is less than 2 or number modulo 2, right, which means if it's even, num modulo 2 is 0, then we return false, right? So we cover a couple base conditions, and by covering those base conditions, we can then go from the divisor in the range from 3 up until half of the number plus 1 going by 2s. So you imagine we're going 3, 5, 7, 9, 11, right, etc. And if in any case the number is divisible by the divisor, then we return false. Otherwise, we return true. So we've got is prime up here. This is our helper function, and I'm going to take this. I'll just grab it and I'll throw it into here. And it'll be the crux of find primes. And I'll just solve this one. I think I did just solve this a minute ago, but I'll just solve it again really quick in case you didn't see it before. So I'm going to say for num in nums, if is prime of num, if that's true, then I'm going to make something called primes, and I'm going to append to it. So primes.append to num, and I'll just say primes, that's an empty list, and then we return primes. So I believe that's all that's going to do. I think that was, it's funny because I spent so much time troubleshooting exactly this problem, I believe. Yeah, I solved this problem in the placement challenge. But yeah, essentially all you need to do is create a collector, right? And you know, I'm not sure why this is in this doesn't have to be in the break continue pass challenge, actually. Oh, I see. It's that is prime in this case is using a Boolean flag. That's why we have it there. And if we, you can use a Boolean accumulator. It's really a Boolean flag, and then just return the result of that flag in the is prime function. That's why we have that here. That's not how I did it, but you know, my is prime essentially does the same thing. But let me refactor this just really quick. So let's say we assume that the thing is prime, and if, you know, there are just these cases where we might set this differently, and I'm just going to return prime at the end. But in our iteration, if we set prime to false, we want to break. And the weird thing about this is that I'm going to need to return twice, essentially. So I would still put a return here. Like anytime it's false. This just means I'm not going to want to run this iteration at all. So honestly, I wouldn't use a Boolean flag here personally, although I do see why we're using it in this case. I would just leave this as is, because we're going to immediately return and not have to run all this, immediately return in the case that it's false and not have to build in another logic here. Okay. Let's see. Cool. Okay, so I think that's all. That's all the questions that I'm seeing for now, and we still have a good amount of time. So, yeah, and this twin prime problem, it is a bit tough, right, for basic Python. But it's really the logic puzzle. It's like you've got all the tools you need to be able to do this, and really it's about breaking it down into smaller components and solving each of those smaller components. And in my case, I ended up needing to troubleshoot a bit to come to a good answer. But yeah, it's yeah, some of these can be pretty challenging, and there are multiple ways to solve them. So yeah. Okay, so the question is, you don't have to do this. Let's see. I'm gonna grab a screenshot of. The question is, in this find primes function, whether or not you have to do. Okay. I am just trying to make this bigger. Let's see. There we go. All right. For num and nums, if num less than or equal to 1, continue at elif num is 2, list.append num. I'm not sure I understand the question. Is this in regards to this find primes function over here? Oh, you know what? This looks like... I think I see what you're asking. You're asking whether or not you have to do this part, right? And the thing is, I'm doing this, but I'm using an isPrime function. So I'm using a helper function in order to determine if the number is prime. This is another way you can do it. Yeah. So if we were to write this in... Yeah, let's go ahead and write this in a more procedural way. I'll show you what I mean. So we've got find primes, and let's say we're not using a helper function. I'm going to say for num and nums, and I mean, we can essentially use the logic that you're using here. We can say if, right, if num less than 2, continue. If num is 2, then we append it, right? Elif num is 2, we can append it. So that'll be primes.append num. And otherwise, we check for its primeness, right, each time. So we can say else. Sorry, this is a little bit cluttered over here. I'll just grab it and pull it into my text editor. So this is just a rewrite of find primes where we're not using a helper function. Okay, so you're saying, and otherwise we're going to say for I in the range from, we can go from 2 up to the number, not including the number, of course. If num modulo I is 0, then we want to continue, right, in this inner loop. And we would need a flag here. Yeah. We would actually want to set isPrime to false. And here we're assuming isPrime is true, right? And here we would say if num modulo I is 0, isPrime is false. And we would also want to break. And then down here we could say if isPrime is true, I can just do if isPrime, then primes.append the number. So I think that'll work. And I'll leave this up right there if you want to take a look at it. So let's try that, unless I'm missing something. No, that worked. Yeah, so this is another way that we can use a Boolean flag and use break. And the only reason we don't need to break here, as it turns out, because the for loop will just keep running. We're just breaking because we don't need any more information, right? So we can just break out of the loopage at that point. Cool. All right. So that's a whole lot of stuff about primes. Primes are fun. I have a video. Let me track this down. I'll throw it into the Slack. It's just a project I kind of played around with for fun, just to kind of demonstrate some stuff. Let's look at the playlist. Where is it? There we go. And oh, yeah, exploring windows of prime numbers. I'll just prevent that from playing. And basically, this is just looking at windows of prime numbers. The distribution of spacing between prime numbers. So it's fun. It uses dictionaries. It might be, it's kind of long, but it's coding most of the way through. So if you want to follow along with that, and it applies dictionaries, kind of harkens toward skills that you might see in the technical interview, but kind of digs into primes pretty deeply. So I'll just put that in the Slack. Exploring windows of prime numbers. Variance and standard deviation. So let's see. Let me just grab something here. It's great that you all are asking so many questions. I'm not even sure if I'm going to get to variance, the stuff on variance today, but that's okay. It's good. So challenge 3 of dictionary accumulators. Let me snag that, and okay, so dictionary accumulators. These are super important for the technical interview. This is where you want to have a lot of strength, and we're looking at challenge 3. Okay. Oh, let me, before I do the dictionary accumulators, I'll just back up really quick, and let's see. Let me, okay, in this find primes, the question is, why can't we use continue, and instead we use break? Well, if we use continue here, it doesn't really mean anything. If we use continue, we're just going to go back to the beginning of the for loop, and we're going to check the next number. But if we've set as is prime to false already, we just don't need to do any more in this for loop. Like, the for loop is done. We don't need to check the next number for divisibility, anything like that, because we already know that it's not prime. And so we can just break out of the loop entirely. If we use continue, then we're going to go back to the beginning of this loop on 96. We're not going to go back to the loop on 89. We're going to go back to the loop on 96. So we actually want to break out of this. But the thing is, we don't even have to. This will work without breaking it. We can just do that. But it's just better to break it because we don't need to perform any more iterations there. Okay, so let's look at this dictionary accumulator problem. Challenge 3. So write a function. We're being very polite here. We're saying please. Please write a function. Called accumulator function. It's a good name. It's exactly what it is. Accumulator function that takes a list as an input. Okay. Any old list, which I'll name LST. This function should return a dictionary containing keys representing all the different items in the list, and values representing the number of times that key occurs in the list. Okay, so this is sort of an abstract of so many things that we will ask you to do with dictionaries. So I'm just going to make a generic empty dictionary called D, and I'm going to say for each item in the list, if we're going to assume that the items are scalar values to start with. Like, we're going to assume they're not lists or dictionaries or something else. So we're going to say if the item is not in the dictionary, then dictionary sub item is going to get primed with that. So I'm going to just set it to 0. That's our count, because our values are counts. And then we're going to increment that. And we're going to increment it no matter what, right? And Yeah, if there might be something that we're not describing well here. So I'll test this, and if it doesn't work, we'll dig into it, and we'll look at the errors first, because sometimes we're trying to get you to examine the errors to see if you can come to a solution, but sometimes we also don't give a very good description, unfortunately, and we do our best to go back and correct that when we don't. Okay, so this worked, and let me show you an alternate version of this code that means the exact same thing. So this is a dictionary accumulator. I initialize the dictionary is initialized here, same thing, right? And for each item in the list or each value in the list, either way, if the value is in the dictionary, then you increment it. Otherwise, you set it to 1. The difference I'm doing here is I'm saying if the item's not in the dictionary, then we initialize it to 0 and we set it to 1. But the logic's the exact same, comes to the exact same place. And so you're getting an assertion error for the last 2 challenges. Do you want to post your code for challenge 3, and I can go through and solve this challenge 2 really quick, and maybe we can figure out the wall that you're hitting, and then I can ask some sample questions that we might ask on the statistics concepts for the technical interview. I can definitely do that. Okay, so let's see. Do I have that down there? Yeah. I'll just go ahead and delete this then. Okay. So the question: write a function called modulo dict, and I usually just, I'll just start off with the function header. Take a single number as an argument. Okay, so that's some number. This number will be used in the modulo operation. It should calculate I'm assuming the function, modulo dict, should calculate the modulus using the argument of every number from 0 to 100, not inclusive of 100. Okay, so I'm going to say, oh, okay. Well, I'll just wait a second, but I know that I'm going to need something like this, range from 0 to 100, right? Okay, the keys will be the possible modulus values. The result of the modulus of the number, of whatever value is here divided by the number, right? The keys will be possible modulus values. The values will be the count of times that modulo value occurs. Okay, easy enough. So we're going to make a dictionary, and I'm going to say for val in range from 0 to 100, if how about I'll make something called res. This is the result of modulus. This is going to be val modulo num. Res gets val modulo num, let's say. And I'll do that same logic. If res not in D, then D sub res is going to get 0, and then I'm just going to increment this. So I think that's all it's asking for. And let's try this. This is kind of interesting for kind of number theory problems, right? So I'll print. Actually, I'll do this for k v in modulo dictionary on, let's do 3 dot items. Let's return. Let's print K and V. And this makes sense, right? So we get 3 divisions. We get modulus 0, divisible by 3. We get modulus 1, where we have a remainder of 1, modulus 2, where we have a remainder of 2. And there are 34 times between 0 and 99, inclusive of 99, or 0 to 100, not inclusive of 100, where the number is evenly divisible by 3. So I think that's what this is asking for. Let me go ahead and test this before I assume that that's correct. Yeah, that's correct. And this just gives us kind of an analytic lens. If I do modulo 5, how many key values do you think we'll have? Turns out we'll have 5, and that makes sense. This is pretty informative of kind of discrete math and of things in discrete math and things in number theory. But cool. Sorry, dog's barking. Okay. I'm not sure where your assertion error is coming from, but if you paste in your code, we can take a look at it. Otherwise, I'm going to jump over to some sample questions that you might see on the technical interview. So let's think about that. So in general, right, we've got this warm-up section, and if you get through the warm-up in a reasonable amount of time, then we're going to assume that you're ready to take on the main problem. The warm-up usually has you writing a couple of simple functions and then doing some stats problems. I'm just going to kind of wing it and ask the kinds of problems we might ask you. Yeah. So let's say let's think of something related to a base 4 number system, just for fun, right? Oh gosh, is this how I want to do this? Yeah, this is how I'm going to do it. Okay, let's say you have a base 4 number system, right? And just to give you some insight here, that's going to go, if we're counting in base 4, we're going to go, let's say 0, 0. Here, I'll do this first, so I don't have to comment things in and out all the time. We might go 0, 0, 0, 1, 0, 2, 0, 3, and then we would roll over to 1, 0, 1, 1, 1, 2, 1, 3, and then 2, 0, and so on. So that would be base 4. I might, let's say I ask you to write a function that returns a random value, a random base 4 value, and that's going to be between 0 and 3. So, 0, 1, 2, 3. That's 4 numbers. That's a base 4 system. So if I'm asking you to return either a 0 or 1 or 2 or a 3, then I can go ahead and use random choice. So I might say from random import choice, and I might write a function called get, I don't know, I don't know what you'd call get base 4 value, but that's just a long name. I'm just going to call it a quad. I'm sure that's not what it's called, but that's okay. I don't need a parameter here because I'm just getting a random value, right? So I'm just going to return the choice, and I can do this a couple ways. I can return the choice from 0, 1, 2, or 3, right? I could do that. I could also do the list of the range from 0 to 4. Either way, that should work. So I'm going to print get quad, and this should get me a value between 0 and 3. 3, 1, 1, 0, 1. Yeah, I mean, we can see it works, right? So that's working. And then maybe I want a function. So write a function that returns a list containing, let's say, a list of length n containing random base 4 values, something like that. So I'm gonna write, I'll just call it quad list and let's say we default this to 6. So it's gonna be a length 6 list by default. I can say, I'll just make an out list, and I can say for whatever in range n, and the reason I'm using an underscore here is that we don't need that value. So I might do that, and I might say out.append, and this is going to be one of these quaternary values. And then I can just return out. Okay. So we've got that. And I can just call out to this. And let's say we want a 16, a length 16 list of quaternary values. And I get a function out of it because I did not call the function in here. So I just got a bunch of functions. But I fixed it, so now we get 3, 0, 2, 3, 3, 3, 2, 2, etc. Right? So that looks like it should work. And that should be fine. Okay. So let's say I ask you the question, consider a random variable, let's call it v. V represents the sum of a randomly generated quaternary list. So a list like what we just generated, and let's say of length 16. Okay. And is that what we want to do? Yeah, let's say that is what we want to do. V represents the sum of a randomly generated quaternary list. And so let's think about that. Let's print some potential sums here, okay? So let's print the sum of a quad list of length 16, 28, 20, 24, 25, 20, 17, 26, 23, right? We're getting a whole lot of values, a lot of them in the mid-20s, right? So what if I asked this question? What is the probability that V equals 0, right? I can also write this as what is P V equals 0, right? So what is the probability that random variable P, that random variable V equals 0, given this scheme? So think about that. There are some ways we could approach solving this, and it turns out there's actually a fairly easy way to answer this. So think about it and try to answer it. And I'm going to sidestep for a minute while you consider this. I'm going to go ahead and take all of this and put it up here in the corner. And I'm going to switch gears and answer another question and come back to this. So this is actually a lot like something you might see on the technical interview. It's not exactly from the technical interview, but it's something that looks like something on it. Okay, so let's jump over to, I'm going absolutely nuts. I can't get the code to run in the final beginner challenge from earlier. Okay. Let's run through this. This looks like it's actually just probably a troubleshooting error. Okay. Could it be that? Equals plus? should be plus equals. Is it possible that that's because I definitely think that that wouldn't run as equals plus. It would have to be plus equals. So I think that might be where you're running into an issue. I think the rest of this looks fine. Yeah, let me know if that's not the issue, and we'll come back to it. Okay. All right. So you know, maybe you've been thinking about this a little bit. You've been thinking about this a little bit. What is the probability that v equals 0? And those kinds of errors are the worst, by the way, because, you know, unless your text editor is telling you, hey, you have an error here, it's impossible to see it. And I have a weird gift to see those kinds of errors. Does that make sense? Like, most people can't see those errors easily. They just jump out at me. Other things I have a harder time troubleshooting, honestly. Some things that people find really easy to troubleshoot, I find really hard. But those kinds of like weird errors, right? Really obtuse little errors, they just jump out at me for some reason. Okay, so we're wondering, what is the probability that v is 0? And to give a sort of foundation in logic here, if we are thinking about this in a counting pattern, we have a base 4 system, and we're dealing with 16 numbers in that base 4 system, a length 16 number. So the first number is going to look like this. The initial value is going to be, so I think that's 16. And our next number is going to be this, right? And our next number is going to be this, and our next number is going to be this, and then our next number is going to be this, and so on, until all of these numbers are 3, okay? So what does that mean for our sums? What is the probability that v is 0? Well, the only way that the outcome, this sum of numbers, the only way this can be 0 is in this first value, right? This first list. This is the only way. So we can start thinking about this as 1 over something, right? So this is 1 over something. And what I would say is this is 1 over everything from you know, all zeros to this number. This is our maximum number, right? I could print the sum of this. What is this? It's just 16 times 3, so what is that? 48, right? So 48 is also 1 out of however many values there are here, right? So this is, if we could just figure out the length of this list, then we'd be sitting in a good spot. Turns out the length of this, if we're considering every possibility, right? There's 4 possibilities here. And we're going to have 4 more, right? That include 1, and then 1, 0, 1, 1, 1, 2, 1, 3, 1, 4. Then 2, 0, 2, 1, 2, 2, 2, 3, 2, 4. And ultimately, we could consider this in a counting pattern, right? If this was binary, then we'd only be considering these 2, and we could float 1s across the whole thing. It would turn out that we'd have 2 to the n values. So in a base 4 system, we've actually got 4 to the n values. Okay, so this is actually 1 over 4 to the 16. And that would be the probability of getting just this value out of all the values. And so that's going to be a pretty small number. Let's see if we even have the precision to see that number. Okay, we do. That's a tiny number. It's really small. That's fine. Let's let's consider just this. Let's just take a look at the size of that number. That's a pretty big number. Okay. Now, what if I asked you a different question that is maybe a little more involved? Right, here we're just asking what is the probability that v equals 0. If I were to ask you what is the probability that v equals 27, that would be a harder question to answer. In fact, I'm not sure that I would want to answer that question. How many times are these different arrangements, right, these different permutations, how many times are they going to add up to 27? Yeah, that's just a harder question to answer. Now, how would we approach answering it? I'd probably take a sampling approach, personally. There are other ways that we could approach it. Like, I could, what is this number? 296. Was this 4,294,967,296 times? I could write a for loop with with 16 nested loops, or a for loop with 15 nested loops, and we could do this count. Let me just, should I do that? Oh gosh, here. Why don't we do this? Why don't I see just how long this is going to take? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. This is nightmarish. Don't recommend anybody do this, but we're going to take the sum of I, J, K, L, M, N, O, P, Q, R, S, T, U, V, W, X. Is that 16? 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. Okay, great. We only need to go through T, apparently. So let's do I, J, K, L, M, N, O, P. Oh, geez, it's not. Okay, we need a few more letters in there. V, W, we need to go through X. All right. Apparently I don't know how to count. Okay, U, V, W, X. All right. So if the sum, well, let's get the total, right? Just verify my math here. So total is plus going to get 1. And let's call this sum to 27. Start that at 0. And we can just ask the question, if this equals 27, if that's 27, then then we run out of room on the right side of our text editor, right? So we can divide this sum to 27 by the total to answer that question. So let's see if this will even run in any kind of reasonable amount of time. I actually think it won't take too long, but I could very well be wrong. So let's find out. Make sure I'm not printing anything else. Okay. So again, we're trying to figure out the probability that v equals 27 in a randomly drawn number from 16 length quaternary, the sum of 16 length quaternary. Okay, let's just find out. Okay, I'm gonna let that think for a minute, and it's probably intractable in this approach. So, this is the kind of question, there probably is a closed form way to answer this, but what we'd probably do instead is get a random quaternary number and do this. Where are we doing this? We can get a random quad list, right, of length 16, and we could pack it into a dictionary. So I might make a, so get quad distribution, and do n is 16, num samples, and let's do 100,000 samples. 100,000 is a lot less than 429 billion, 42, wait, 4 billion, right? And we could say, let's just make a dictionary. So D gets dictionary, and we say for whatever in range, the number of samples, and I'm hoping by the time I finish writing this function, this operation down here will have ran its 4 billion times. We'll find out. So I'm going to say for whatever in the range number of samples, I'm going to call out to our quad list with our length, which we're assuming to be 16, and I'm going to say, just the sum of that is what we're interested in. So this will be, I'll call it quad sum, and I can just ask the question, if quad sum is not in the dictionary, then we can say D sub quad sum, set that to 0, right? Same pattern, plus gets 1, and we can just return the dictionary. And what this is going to give us is a dictionary from which we can derive probabilities. So, that's kind of nice. We're going to be able to use that eventually. I might have to kill this 16 nested loop, which nobody should ever do. We're never going to ask you to to do something like this on the technical interview. I'm just demonstrating a style of problem, right? Where in this scheme, it's easy to answer the question, what is the probability that v equals 0, where v is the sum of this quaternary. It's harder to answer the question, what is the probability that v is 27? So we can do this quad distribution. Let's go ahead and think about this. So in this case, we would take D sub 27 and divide it by 100,000 in order to get the probability, right? And I hope that makes sense, right? We're looking at the counts of some of these different possible outcomes. And since we're doing this 100,000 times, we should assume that those counts add up to 100,000. And, you know, if we do that, we should be able to reasonably, you know, project a probability here. You know, estimate a probability through the sampling approach. So the kind of thing we would ask on the warm-up is not for you to do this thing on line 33, but to be able to intuit this approach. Really, we'd be asking something like this. What is the probability that V is 0? And then what is the probability that V is not 0, right? Let's think about that. What is the probability of V not equal to 0? Well, that's just one minus all of this, right? So we might ask you random variable questions. We might ask you some fairly straightforward probability questions, right? We might ask you a Poisson question or two if you get the Poisson interview. The interview that covers Poisson is very much about the Poisson distribution, right? Where you'll have to write factorial, and you'll have to write the Poisson PMF, and you'll have to write the Poisson CDF as well. And then you need to answer a number of questions like, given a busy subway station, what is the probability that, you know, given that you expect 5 people to walk through every 10 minutes, let's say some turnstiles, what is the probability that's not that busy, is it? Let's say you expect 50 people to walk through every 10 minutes. What is the probability that in 20 minutes, 40 people walk through? Like, those are the kinds of questions that we're going to ask you in the warm-up. The main problem is pretty divergent. So there's a question here, what's a reasonable amount of time to finish the warm-up? We usually say aim for half an hour, and we're going to let you know at the end of the warm-up if we think you need to come back in order to be able to successfully complete the main problem, right? We'll let you know, because we see the warm-up as, you know, you get through the warm-up and then we're clear that you're ready for the main problem. If it takes you a little bit too long, if you're not going to have enough time, then we're going to say, hey, you know, study some of this up a bit more and come back and we'll give you the same interview. And the warm-up will be exactly the same as before. So you'll be able to go through it much faster. The assumption there is that you're taking time to study up your Python and get to something, get to a more proficient level. This massive nest of loops might not actually complete in a reasonable amount of time, and we're at the end of study hall. So let me see. Let's see. Oh, cool. It looks like the last problem that was put in there, the last question that was put in there, other people answered. So that's cool. Yeah. So I'm just gonna say never write a nested 16 for loops. Apparently, even on a pretty decently spec'd computer, this isn't going to run in a reasonable amount of time. But let me just demonstrate this other. So I just killed that loopage because, you know, no good reason to write that. It's an intractable problem. If there's a closed form solution to figuring out probability of v equals 27, great. But let's consider a sampling approach, and let's see if we can get to an answer. So D is going to get this. 100,000 might actually be a bit much as well. Let's see. That might not run in a reasonable amount of time, but it might. Oh, no, it did. Okay. So so look at that. we just sampled 100,000 times, and our estimated probability for this through a sampling approach, this is an estimated 0.0732, the probability of V being 27. So out of 100,000 times, V was V equal 27, 0.07328 times 100,000, right? So that actually seems fairly probable in our distribution. If we wanted to take a closer look at the distribution, we could just take a look at it. Why don't we do that? So I'm going to say for k, v, and d dot items, let's print the f string of k and v. Oh, I should probably sort this because it's going to be out of order. And this is going to give us a clear idea of the distribution of these values. Now remember, this is out of 100,000 calls. So let's see. We never achieved 48, right, which is our highest value for a 16-bit quaternary, right? 30 plus 18, right? Yeah. So 48. And we never achieved 0 either. The lowest number we achieved was 6 for the sum, and that happened 2 times. So it's kind of nice in these middle values. We're going to get some estimated probabilities that look more like what the real probabilities, what the theoretical probabilities are, but without taking that nested for loop approach or finding some other closed form approach, we're going to have a hard time actually finding out the true probability. But no biggie. We can get a reasonable estimate through the sample approach that we took here. Okay, that's it for study hall today. I imagine tomorrow, Thursday, we're usually up until maybe a month ago, I was doing presentations on different data science topics, but we're coming up to interview deadlines. And so I'm probably just going to do a study hall tomorrow and, spend some time like we did today, looking at the kinds of problems we might see on the technical interview, and kind of doing some exploratory coding, helping you solve problems in the Learn materials. And I'll probably put off the latent topics show for a couple more weeks until we get past the interview deadline. So it'll kind of look like unofficially it'll be 4 study halls a week, right? Monday, Wednesday, Thursday, Friday. Officially Monday, Wednesday, Friday for the next few weeks. So yeah, thanks so much. Bring any questions that you don't get solved in the meantime, bring them to our study hall tomorrow or Friday. And same time. It's 4 p.m. Mountain, 3 p.m. Pacific, 6 p.m. Eastern. And thanks so much.